about the environment here, and we're going to focus a little bit more on some broad topics, okay, that will be important as we go throughout the last 3 days of this unit. So we're going to talk about moist air, something called a psychometric chart, and then we're going to get into atmosphere and barometric pressure. Okay, so here we've got what's called a psychometric chart. Okay, there is a lot going on here. We've got 4 different variables. Okay, and so just to highlight each of those, we've got humidity. We've got wet bulb temperature, and I'll explain what that means in just a second. We've got water vapor pressure, and then we've got dry bulb temperature. Okay. And so what this chart does is it allows us to figure out how much water the atmosphere can hold at a given temperature. Okay, whoops, sorry, I went back. So for a given temperature, which is here, this dry bulb, I'm trying to, it's right here. Okay, so 30 degrees. If we're at 100% humidity, which is right here up at the top for 30 degrees, okay, so just to kind of give you an idea. So right there, if the dry bulb temperature is 30 degrees and the wet bulb temperature is 30 degrees, that means we're 100% saturated. In other words, the environment is holding as much water in it as it possibly can. Okay. Notice that as we go lower and lower, this outside line here, right here, this curved line, sorry, I'm not drawing it very well, that's where 100% humidity exists. Okay. Notice that as we increase or decrease temperature, the amount of water the atmosphere holds reduces. Okay. And so if you think about it, oftentimes in the winter, this is where your skin gets really dry, your lips get really chapped. Even though it's cool, the reason being is that the atmosphere just doesn't hold as much water. Okay. And so it makes you more susceptible to having dry skin. Whereas the hotter it gets, it can hold a lot more water. Okay, so each of these lines here that are kind of going up that curve, like see where it says relative humidity, each of those lines, that represents the percentage of water the atmosphere is actually holding. Okay, and so what's 100% saturated, which is here at 25 degrees Celsius, so at 25 degrees Celsius, we're in the mid-70s. Okay, so at 25 degrees Celsius, what is a 100% humidity would only be 20% humidity if we come out to 45 degrees Celsius. Okay, so we'll go over this a little bit more detail in class. I think it's easier to do a worksheet on this, but a psychometric chart helps us to understand the relationship between humidity, water vapor pressure, okay, or the amount of water in the atmosphere, and then the temperature outside. Then we've got partial pressure. I feel like, I hit too many buttons. And barometric pressure. So pressure is just how much force for a given area. And so we've got atmospheric pressure, generally measured in millimeters per mercury. Okay, and remember the air has weight. Okay, now at sea level, this weight is 760 millimeters of mercury. Oftentimes it's referred to as 1 atmosphere. But atmospheric pressure changes with elevation. The higher up we go, the lower the pressure. Weather, climate, clouds, however you want to think about it, that can also change pressure. When you watch the news, they talk about, we've got a high pressure system, we've got a low pressure system, that sort of thing. That will also change it. So atmospheric pressure in a specific location changes due to what's going on with the weather. And then it also changes with latitude. Okay, so the pressure decreases the further you are away from the equator. There's kind of a big bulge of air around the equator due to a variety of factors that we're not going to get into that much. Okay, so how are these 3 things related? Well, as we go down in elevation, as we go up in elevation, ambient pressure goes down. So they have an inverse relationship. Remember, gas composition doesn't change with altitude. Wherever you're at on Earth, it's 21% oxygen, okay, and about 78% nitrogen. Obviously, there are a few other things, but for the most part, it's nitrogen and oxygen. This is true at sea level. This is true on top of Everest. But the problem is the amount of air decreases. Okay? And so we can see how this affects things by using Dalton's Law. So remember, Dalton's Law is the total pressure of gases in a system is determined by the individual partial pressures. Okay, so the pressure of oxygen would equal the fraction or the percentage of oxygen in the atmosphere times the barometric pressure. Okay, so for example, if it's 760, and we're just going to make the math easy here, so we're going to say it's 20%, that would mean the partial pressure of oxygen is 152 millimeters of mercury. All right, so when you go up in altitude, there's less air. Because there's less air, that means there's going to be less of each of the gases. So here gives you an idea of how barometric pressure or oxygen equivalent changes with altitude. Okay, now if we had a lot of money and had a really, really fancy environmental chamber, what we would do is we just press some buttons and it would actually pull pressure. It would decrease the pressure inside the chamber. It would be called a hypobaric chamber, and that's all we would do, and we'd be able to simulate altitude in a hypobaric condition, which means less pressure. Those are very expensive. They do exist. They're really expensive. And so we have what's called a normal baric chamber. And what that means is we can't change the barometric pressure, but we can change the composition of the air that's inside that environmental chamber. And some of you are doing a study for 488 students where they're having you go to, I think, 2,000 feet. Okay, so here it says Eugene. You can think Terre Haute. They're both very close to sea level. Okay, let's just say we want to simulate going up to like Machu Picchu, which is 18,000 feet. Well, in order to simulate that, we need to change the composition of the air inside that chamber so it's only 11% oxygen. So basically cut it in half. If we cut it in half, that will give us about similar to 18,000 feet. Okay, and so there's some things in the works where we might be simulating Mexico City, and so when we're at if we do that, it'll be about 16% oxygen inside the chamber. So this leads us to the ideal gas law, and it's called ideal for a reason. So this is kind of like perfect situation. So we've got the pressure, and the product of the pressure and volume equals the amount of gas. It's measured in moles. Okay, and if you've never had chemistry, you've probably never heard that, but just think N is the amount times a constant, and then it's multiplied by the temperature in Kelvin. So what does this all mean? Well, there's a couple of things that I want you to remember here. And really, we can not even worry about this, because these numbers are going to stay constant. The amount of the gas is going to stay constant, and the constant is going to stay constant. And so what it means is that, one, if pressure goes down, then temperature goes down. If pressure goes up, temperature goes up. So think about this from an altitude point of view. Okay, at the top of a mountain, I have low pressure. What's also going on with the temperature? You have low temperature, right? It's much cooler on top of a mountain than it is at the bottom of a mountain. Okay, now what we also have, and it's not really included in here, but if temperature goes down, we have increased density. Okay, and again, this is nothing else changes, but if we increase temperature, we have decreased density. So to tie this all together, whoops, hit the wrong button. I want to focus really on this reduced pressure leading to reduced temperature. Okay, so notice here we've got altitude in feet and temperature in Fahrenheit. Okay, we're saying that we're on the same spot in the Earth, right? We're not changing latitudes, that sort of thing. All we're doing is changing altitude. Well, notice that as we go up in altitude, temperature drops. And it drops by 7 or 8 degrees Fahrenheit for every 2,000 feet. Okay? And so here at sea level in Terre Haute, we'll just say that on today when I'm recording this, it's pretty close to about 60 degrees. Well, if we were at 16,000 feet in the air, it would be closer to 2 degrees. Okay, so just going up, I guess it's about 3 miles, has a significant effect on temperature. And so that's where we're going to end kind of this basic overview of the environment.